Hello everyone and welcome back to AP Biology with Mr. Jennings. Today we're going to talk about water in the second part of this chemistry basics. So water is kind of an interesting substance. It's very wild when we talk about it in the terms of chemistry. It's got a unique chemical behavior that's linked to its structure and its overall chemistry. As we discussed in previous videos, water is a polar compound. Water is the result of uneven distribution of electrons between the oxygen, that's highly electronegative, and the hydrogens, which is actually very lowly electronegative. And because of this, water not only is it a polar compound, it's also got a really unique molecular shape that most of us are familiar with. So usually we see water rendered like so, with hydrogens down here on the bottom corner, and oxygen being the much larger looking atom. And that actually is what we like to talk about as the molecular shape. This is what we call a bent structure. And what this does is create what we call a distinct dipole effect. Dipole meaning two poles. Think magnets. So much like a magnet, we have these two distinct poles. We have a slightly negative pole and a slightly positive pole. These are capital deltas, by the way, if you're wondering, and they look like 8s because I do not draw Greek letters very well. But because water's unique polarity, not really unique polarity, but because of water's polarity and unique molecular shape, this combination of two things results in a very unique compound that has a situation that creates a lot of hydrogen bonding. A tremendous amounts of hydrogen bonding is going on with water. And this is what's going to go into water's properties. So in today's video, we're going to mainly focus on the properties of water and what makes water so unique and what makes it so important to life. So the first property of water we like to talk about is cohesion and adhesion. And I actually use this PowerPoint slide here as an example of this. So if we look here, up here in the corner, we see water droplets. This is a great example of one of water's unique and special properties. And I keep saying the word unique because it's not true that most chemicals have some cohesion and adhesion properties. I mean, we have adhesives, that's literally their name. But water has some specialness about it, and that is this cohesion. Water likes to stick to itself, and it's really cohesive. That's why we see water droplets all the time. That's a great example right here. So you pour some water onto a table, it's going to beat up and to form these little balls. That's all due to these really strong intermolecular forces between water. So water here is, again, slightly positive and slightly negative. And it comes along with another water that is slightly positive and slightly negative. And the positives and negatives are attracted to one another, creating what we call hydrogen bonding. Well, when you get enough of these together, they're going to pull together really tightly. And that's what results in these droplets. Now, the same property explains adhesion. So, you take the container, we're going to put this in a container now. Well, the container itself is actually made up of tiny little molecules. And more likely, if you're dealing with plastic, it's going to be a lot of carbohydrates, same with glass. You're going to see a bunch of little carbohydrates. Well, everywhere on here, there's going to be some areas where hydrogen bonding can also take place between the water. So water can go along here and do a little bit of hydrogen bonding to the sides of the container. And this is what creates adhesion. It's when water sticks to the sides of its container. Now, these are very important properties when it comes to plants. Plants have no central circulatory system of their own. So for a tree, so we got a tree here. For water to go up from the roots, it has to take advantage of what we call capillary action, which is the more narrow the xylem is, the fluid-containing vascular tissue of a plant, the more likely water is going to travel up it by adhesion. This is a very important property, and we'll talk more about this when we get into matter proper. But this is a really interesting property, one of the most important properties when it comes to life. Now this property is high specific heat. This is actually not only is an important property for life, it's also a very important property for this planet. See, it takes a lot to get water to move in its temperature. It's a common idiom to hear, watch pot of water never boils. And if you ever sat in a chemistry lab long enough to try to boil some water, you understand that sentiment altogether. That's because water contains this property of high specific heat. And specific heat, if you don't know, it's not necessarily high specific, but specific heat in general, if you don't know, is all about how much energy it takes to be either absorbed or released before it increase or decrease, respectively, in the temperature. Higher the energy absorption it takes for the temperature to increase is a higher specific heat. So some examples here, we have water. All right, so water has a specific heat of 4.18 joules per gram centigrade or Celsius. Now, the units may not mean much to you, and really they're conversion units, but give it something similar to ethanol. Now, ethanol is a common drinking alcohol most of us are familiar with. Its common one form is distillation. It is almost 4 times as less high of a specific heat. It takes that much less energy for ethanol to convert or move up a degree in temperature. Then we know something even more different, which is iron. Iron is a metal. It is not a covalent compound. It is actually a metallic compound. They have their own unique chemistry, and their specific heat is so low it's almost barely registers, 0.44. That means it doesn't take a lot of heat to get iron to increase in temperature and decrease conversely. And that makes sense. Iron is a substance that is highly conductive of heat. That's one of the unique properties of metals. But this high specific heat is really important for the planet. So our planet is mostly covered with water. Water takes a long time to heat up and cool down, especially that much water. If you don't know this for sure, take a small glass of water, put it in the freezer, and take a slightly larger glass of water, put it in the freezer. You'll notice the smaller glass takes less time to freeze. It makes sense. More mass matters when it comes to this. While water, since it covers most of the planet, takes a lot longer for it to heat up and cool down. It helps regulate the temperature. It is a nice temperature buffer. It's also why you can go to the beach in April or early May, and if you step in the water is still really cold. It takes a while for that water to heat back up. It's also really what's interesting whenever you hear people talk about the global water temperatures rising upwards of like 1 or 2 degrees Celsius. It takes a lot of energy for it to go on, so it really gives you an idea of how much energy is actually going on here. Now, speaking of water and its oceans, not only does it help keep the planet, relatively stable temperature, water also has this unique ability to float. And that sounds stupid. Most of us know ice floats. But think about this. It's really insane. Not many other substances in their solid form of matter float on the liquid form of matter. And that all deals with this idea of kinetic molecular theory. So what we do is you have a bunch of particles, and they're constantly moving around at different speeds. And the general rule of thumb is, the warmer the substance is, the more energy it has. The more energy it has, more particle movement. That's kinetic molecular theory in a nutshell. Well, typically, in solids, most of us are taught that solids, the particles just sit there and vibrate in place. Not very much energy. And that results in this really densely packed substance. Alright, so we have these really densely packed substances. As they get cooler, things tend to condense, and when they get warmer, they tend to spread out. That's thermal expansion. Water sees this and goes, no. Water, when it gets cold, because of its hydrogen bonding, it actually creates a crystalline structure that gives spacing in between each of the water molecules because of these intermolecular forces, causing water to expand as it freezes. And if anybody have ever left a bottle of water or a soda in the fridge too long, you've learned this. The freezer too long, you've learned this the hard way. Now, what makes it important for life on this planet is the ice sheets, the glaciers and ice shelves and all that really matter because they help reflect a lot of temperature. And the ability to float keeps them on top of the surface. That extra white surface creates a really great temperature reflection. So as those levels decrease, it makes it a lot warmer on this planet. That's not a good thing. Now, another unique property of water And probably one of the most important for chemistry, is that water is what we consider a universal solvent. And I'm using quotation marks here because it is not truly a universal solvent. Not everything dissolves with water, but most things do. And if it doesn't, just maybe you have to heat it up a little bit, and it usually works really well. Water dissolves almost any polar covalent compound, and sometimes even non-polar ones if you give it a little bit of work, but for the most part, water can dissolve almost anything that's polar and definitely ionic. And that's because water has this unique ability to rip things apart. It comes down to this hydrogen bonding. These slightly positive-negative dipoles really are strong attractive forces to any kind of stable molecule. What seems to be stable can be ripped apart relatively easily. Now, one thing it cannot really affect is nonpolar compounds. That's your oils, waxes, and lipids in general. And they have really struggled with those. And that makes sense. You always hear the phrase, like water and oil. They separate. They keep themselves apart. It's not only just a density thing. It's a molecular forces issue. Water literally cannot do anything with polar compounds. And this is very important in not just chemistry. The whole field of organic chemistry is really concerned with this. It's also really important when it comes to your cells. And we'll talk more about that after we get through evolution. So here in about a month or so, in class time, you're going to hear more about why water's polarity matters on a cellular level. Now, one other thing water does, and it's really important for chemistry, is water's so strong of a solvent, and that creates really strong dissociation. Water can actually rip other water molecules apart. That's the dissociation. So water disassociating itself means it can rip other water molecules apart into two separate ions. It rips them into either a hydrogen ion or an OH or a hydroxide ion. So we don't really see this on itself, by the way. Typically it recombines with water to form what we call hydronium, which is H3O positive. H3O positive is water with an extra hydrogen ion floating around with it, and then there's also hydroxide. Now, acids are compounds that donate protons, and bases are proton acceptors. We're getting into a little bit more of a Bronsted-Lowry definition of an acid and base, and that is definitely probably beyond what you really remember from definitely like middle school chemistry level stuff and physical science. You may have talked about this in chemistry, but it may have been in passing. So, the big thing to remember is acids are the things that donate these protons, as you see here, and bases are the ones that accept the protons. Now, one thing you ought to be able to do is with pH. We'll talk more about this in the future. pH is a measure of acidity. To calculate pH, you just need to do the negative log function of the concentration of hydronium. And let's make sure we take a note here. So the negative... So, whenever you see something in brackets, this means concentration. So when you see a chemical compound in brackets, that's saying you're going to take the concentration of that substance. In this case, we're going to take the concentration of hydronium and do the negative log function of it. Not that complicated. You could use a calculator on the AP exam and obviously the exams in class. Now, let's say you're not given the hydronium concentrations. Excuse me, guys. So say you're not given hydronium concentrations. You're given hydroxide concentrations because you're dealing with a more complicated problem. That's where this little equation comes in at. So this equation here is basically a plug and chug. You plug in the variables you have and figure out what you don't have. And then you can do the negative log function to figure out what the heck the pH is. Alright. Now, pH matters in life. So the reason we concern ourselves with acidity and chemistry and all these chemical compounds when it comes to biology, besides the fact that biology is, again, applied chemistry, is that it dictates how life works. And pH is really one of these very, very important compounds. It's a very strong limiting factor for most organisms. Life tends to prefer a narrow range of pH, and we're one of them. Humans have a buffer in our blood that keeps our pH at a relatively somewhat basic neutral level. We don't like to be too acidic. Life tends to prefer that. They try to prefer, most life forms will tend to stick around a neutral area, anywhere from 6 to a little over 7 pH, and really 6 is pushing it. So they like to really stick around there, pH of 7. Now, what happens in these situations, though, is extreme variations are disastrous for life. And this picture here is actually something really disturbing. So this here is a projection from the NOAA, the very important weather organization here. And they say about the current trends of the planet's acidification. That is basically the oceans are getting more acidic over time due to pollution and acid rain and temperature. So as oceans continue to become more acidic, by the year 2100, snails' shells, and this is what you see here, this is a replication of a snail shell. Snail shells are made out of calcium carbonate. It's a substance that will chemically react with acid to neutralize the acid. It's a basic compound in a way. Well, when you put a seashell in acid, it tends to not dissolve. It tends to react and disappear. So by the year 2100, they're estimating that seashells of snails and other organisms that have seashells are going to only have about 48 days of life in the ocean before their shells completely dissolve due to the acidity of the water. That is intensely scary. Now, 48 days doesn't seem like it seems like a pretty long time for a snail or slug, but a lot of life forms are highly dependent on these seashells. Hermit crabs and other forms of life really depend on these shells being evacuated by the snail when they die. And the fact that these shells are going to go away, that's going to do a massive cascade effect on the entire ocean. It's something to really consider when it comes to climate change. These things are not made-up numbers. These things are very real and a very scary thing. But it doesn't mean we can't avoid it. So, let's conclude here. Water is one of the most important compounds on the planet. Heck, the planet's mostly made of water, and as life, we're also mostly made of water. We spend most of our time when we look at other planets to look at the water levels of that planet. Liquid water on a planet is very rare. And because of that, though, we like to think about it. We need to think about what those implications are and why does it matter. So we like to look at water's properties, which are all mostly based out of water's chemistry and molecular shape. So water's unique chemistry and molecular shape tends to lend to hydrogen bonding. Hydrogen bonding explains water's adhesion and cohesion. It has high specific heat. It explains how water is considered the universal solvent. It explains how water takes a really great ability to disassociate itself. It explains why we care about it when it comes to pH and how pH is really important for life. So all these factors affect us. Sorry, I also forgot to mention, it allows water to expand as it becomes solid, which is really rare in chemistry. But all these things affect life on this planet. We are an interconnected biosphere. Everything we do affects each other. So every little bit of acids, every little bit of a pollutant, CO2 or sulfur dioxide that gets in the air, affects the life on this planet. And it's something we need to talk about and need to be concerned with, but not be afraid of. It is scary to think about, but not impossible to avoid. If we are aware of it now, we can actually start reversing the processes at this point. Nothing's too far gone yet. But ignoring these things does not make them go away. Alright, that's all that. Next time you're going to see a video about carbon and its unique chemistry and its why it's one of the single most important elements on the planet and why all life is dependent on it, why we have a whole branch of chemistry devoted to just that one element and its unique compounds. Alright, again, thanks for watching. Keep in touch. See you around.